All right. How did they get the picture? Hello, everyone. Thank you very much for coming. My name is Arash. I'm an adjunct professor here at USC. Today, I'm very happy to introduce Stuart Oberman from NVIDIA. He is a vice president of GPU ASIC engineering at NVIDIA. Since 2002, he has contributed to the design and verification of 12 GPU architectures. He currently directs multiple GPU design and verification teams. Stuart earned the BS degree in electrical engineering from the University of Iowa and the MS and PhD degrees in electrical engineering from Stanford University, where he performed research in the Stanford Architecture and Arithmetic Group. He has co-authored one book and more than 20 technical papers. He holds more than 55 granted US patents. I'm very glad to give it up to him. Thank you so much.
Thank you very much for the introduction. So, title of my talk, you guys can see, GPU computing and the rise of generative AI. I have a feeling that people have come to be aware of AI a lot these days. First, there's a seminar, so clearly you've been learning a lot about it, but it's even in our mainstream discussions and dialogues, AI is becoming more and more a part of our conversation. So I think this is good for us to have this conversation. And I'd like to talk to you about some of how we got to where we are today with AI. How did this conversation happen? It didn't just happen from nowhere. I'm going to talk you through some of the journey of how we have gotten to here. And I want to share some of my insights that I've learned as we've gone through this journey. So, some topics just to give you an overview. I'm going to talk about the rise of generative AI. Like I said, I want to walk you through some of the journey, some might say pain and suffering that we've experienced over the past, as you saw, I've been there since 2002, past going on 22 years. How do we then put that all together to build AI data centers? Some example applications that I myself and my teams are really using, and then talk with you about future challenges and opportunities. So that's kind of the outset. I might be dating myself a little bit here, but I don't know. Anyone here remember the movie? Have you ever seen it? You may not remember. Have you seen it? Ferris Bueller's Day Off? Anyone? Okay. So there's a good quote in that movie. Life moves pretty fast. If you don't stop and look around a little bit, you might miss it. Well, that's kind of how I feel a bit about AI. Things are moving really fast, like really fast, especially since like a year ago, December, ChatGPT hit. Now all of a sudden we kind of boom, AI. What's going on? We've got everyone's got an AI chip. You've got an AI chip. You've got an AI chip. Everyone's got an AI chip. What is this all about? Let's see if we can stop, look around a little bit, and see if we can make some sense out of all of it. So to start, here's an example case of using DALL-E 3 text-image generation. Here's an AI-generated scene with the prompt, draw a scene that represents significant changes in our daily lives due to AI advancements, and include that quote from Ferris Bueller. One thing to note is that you can see here that AI isn't perfect. Currently, DALL-E 3 still makes spelling errors. No matter how many times you try, the spelling errors still exist. But this gives a little bit of a notion of, I'm sure many of you have tried all sorts of different AI applications to see what's possible. So clearly, text to image is a really cool application. Here's an example. You probably may have seen this in other talks. What if we asked a large language model, if I were giving a talk at USC for a graduate seminar, what would he present? It actually did a really good job. By the way, I did the talk before I did that slide, but it actually did out pretty well, as it turns out. His presentation likely covered several key areas, giving expertise, evolution of GPUs, NVIDIA's role in GPU development. Let's see, GPUs and AI deep learning, sure, real world application, yep, gonna do that. And some future trends in research, yep, and we'll probably have some Q&A afterwards. And if there are any recent advancements or product launches, to catch everyone up, I was just looking at OpenAI. So here's another example, kind of cool, Northern California, historical footage, all AI generated, all based on the single prompt. If you've been to NorCal, the hills looks like that probably is NorCal. You can see the horses, and how probably really did look in the vintage looking video. AI is really cool and powerful. Multimodal. This is really awesome stuff. Have most of you seen things like this before, I presume? Okay. Let's talk about a little bit, again, where did this come from? If you go back, I'm going to talk about this in a little bit more detail. We started with labeled data sets and image classification, cat, dog. For those of you who can remember going back about 10 plus years, that's kind of ResNet 50 networks. That's where we started. Then came excellent technology. We have transformers. They came about, which then helped us form into large language models. Now we could go unlabeled. Now we have generative AI. Now we have multimodal generative AI, kind of like what I just showed you. Then we have AI where we can put different systems together, different models together. We get mixture of experts models. Most of the big name AI vendors have such big mixture of expert models, along with all sorts of technology for doing high performance inference. So the technology being deployed in AI is moving really fast, just like Ferris Bueller noted in his own coming to maturity, coming to adulthood experiences as a teenager. We're kind of experiencing this as kind of the teenage years of learning what's happening in generative AI. The thing is, when you do all of this, not only do you have all this cool technology, but it didn't come from nothing. It takes more and more orders of magnitude of compute power, both for training and for inference. In this case, I'm showing a chart of training, what it takes for these different models as we have moved progressed over time. So before transformers, we were going in terms of the computational complexity required to train these at about 8x every 2 years. With transformers, really cool, powerful technology, but the technology as we grow the larger networks are growing at about 256 times every 2 years. So all the way up to here at the top is representative of a state-of-the-art mixture of expert large language model that perhaps like the type that you've been using before. So if you recall, which I'll reiterate a little bit later, well, there's 3 things that are really required for AI to be successful. Because again, AI isn't actually, neural networks are not new. You need 3 things. You need the networks, you needed data to train them, and you needed the computational power to put it all together. So we talked about the networks. We have the data has been around now thanks to the internet. So now what we're talking about here is what are the computational requirements to keep fueling the surge in AI and the different technologies. Okay, so that's us stopping and looking around and saying, what's going on here? I would like to say that it didn't just happen. Like we didn't I'll speak with my NVIDIA hat on specifically. NVIDIA didn't just pop out and just say, hey, we can do AI. It actually this happened over a long and grueling, I can talk about my 21 plus years there of hard work that it took to innovate our way with many key decisions and investments and strategies that were deployed along the way so that today here sitting in 2024, we can have these technologies available. So let's go back to the future for a little bit. You heard, I've been at the company for almost 22 years now. For what it's worth, what is a GPU? Just briefly, just to remind ourselves, GPU is a graphics processing unit intended for accelerated computing. NVIDIA introduced the first GPU, the programmable processing unit, in 1999. And it was intended to be a single chip processor to accelerate PC gaming and 3D graphics. The intent when the company was founded was to be an accelerated computing company. And the most readily and straightforward application that could benefit from big acceleration was gaming and 3D graphics. The goal at the time, and still is today, is to be able to approach the image quality of movie studio offline rendering farms, but to do it in real time. So instead of hours per frame, we're looking for 60 frames per second. And with all of the pixels that are there, all of the vertices, if you use standard rasterization techniques, it's considered an embarrassingly parallel problem. It's almost too easy to accelerate, but hey, let's go accelerate it. So we did. We used large arrays of floating point units to exploit this wide and deep parallelism. So one of the first products that I worked on was, you go back in time, I don't know, probably I bet you we have some gamers here. Yeah, no, maybe. Yeah, some shaking of heads. Probably you didn't go back this far. I see a hand popped up on the screen. So you may not remember back to the 7900 time. But this was one of the first ones where we really started to have a focus on efficiency and building efficient GPUs. I'm throwing some numbers in here. You'll see why, but you can kind of keep in mind, we were at about 278 million transistors, 300 gigaflops of single precision floating point performance back in 2004, 2006. Just for, in case you were to buy the OpenGL pipeline sort of block diagram, this is kind of how you would lay onto hardware, how the classic life of a triangle, if you're doing triangle-based rendering, how it would look and why we had these functional units the way we did. Post, vertex processing. Basically, you need to take this mesh of triangles, somehow rasterize them, convert to pixels, and start filling in and shading, texture mapping those pixels. That's what the GPU was built for back in the day primarily, with a lot of memory accesses as well. So you have memory accesses, you have textures for mapping, shading, and then ultimately you would draw things out. So lots of computing horsepower, lots of memory bandwidth. That's something that as we look at these different applications, you're going to say, computing horsepower, memory bandwidth. Interesting, let's keep that in mind. Pre-2005, we used a wide range of numeric representations in the GPU. Inside, their numbers could be in all different shapes and forms, unsigned, different forms, fixed points, floats of different formats, not necessarily anything that was standardized, just numbers that were interesting and made it possible for us to achieve what was necessary at the time to accelerate computer gaming and PC graphics. PC gaming and graphics. Here, I'm showing you this again, 2004, what did things look like? We had, I'll just put them all up here, but there's a point to the madness here. What we had was engines for speaking to memory and getting work. We had a specific set of hardware computing engines for, we had a specific set of hardware engines for doing world space vertex shading work. We had rasterization pipelines, and then we had pixel shaders. These are floating point processors. These are separate floating point processors. And then we had these pixel engines that were setting up the images to then, with high bandwidth, to be able to render to memory. Again, floating point processors, high bandwidth memory. That's what we were doing back then. But they were separate. You saw that we had a world space vertex, we had pixel screen space. So shortly thereafter, trying to be catchy with some titles, was what I'm calling the dawn of GPU computing. Up until this point, this was accelerated gaming and graphics. With G80, which was in 2006, which is the next product that I was strongly working on here, was where myself and our team, we introduced the idea of an SM, a streaming multiprocessor, which you may or may not have heard of, which is an array of simple streaming processor cores, SPs or CUDA cores. They all use the same instruction set, same units, permits better sharing of SM hardware, and it recognized that building these dedicated vertex and pixel shaders would result in underutilization. In retrospect, it seems kind of silly. Why would you do that? Instead, what if you just had all of your different code run on the same processor? Pretty amazing idea. Like, hey, why wouldn't you just do that? Well, because you didn't do that back then, because the workloads, at least apparently, seemingly were very different. But we said, what if you actually just put them all and make them such that they can't all work on a big array of common shared streaming multiprocessors? So we did. In G80, we did that. And keeping things in mind, now we're up to about 681 million transistors. And with the functional units that were designed to run at a pretty high frequency, which has its own story, we were at about 576 gigaflops. The key point here, though, is not only did we put everything together on one unified array of processors for both vertex and pixel processing, but we explicitly invested. We put in extra area to also support general purpose throughput computing, to also support compute shaders. And this was the beginning of CUDA everywhere, which was a mindset of the company, but it didn't just happen. In other words, the idea of doing general purpose computing on a GPU didn't just happen. There were people who were trying to do this by recontorting their code to look like a pixel shader or look like a vertex shader. But we were at least knowledgeable enough to know that that's silly. What if we could make this GPU generally available for C, C++ coding? So that's what we did. This is the array of SMs here. This is a physical architectural diagram. We had units on the top that would do the work distribution for vertex shaders. So you could launch work into this programmable array for vertex programs, for pixel shaders. That's fine, as if they were separate sets of floating point units, but they weren't. They're all the same. But we also introduced a compute work distribution unit so that we could also issue general purpose programs into this array. And if you blow up one of these SMs way back in the day, this is what it would look like. It had an iCache, multi-threaded issue, constant cache, bunch of these floating point units, all interacting with the shared memory, as well as the ability to interact with DRAM. So this was kind of maybe underappreciated, but just from a historical perspective, to realize when we talk about the Ferris Bueller moment, how did we get here? First of all, we enabled compute shaders in hardware. We also had Ian Buck, who had done his PhD thesis on Brook, who brought in the idea of CUDA to have a programming environment in which we can not only have the physical, the hardware capability to run general purpose computing, but we now had a language interface. We had an API that was explicitly for, so you could write in C++ for a throughput computer. New layer type, no problem, we could do that. So now we have the two things that we needed to be able to generally make GPUs available for general usage. We have hardware and we have that API to do it. Going forward, so there's a lot. I'm not giving you every single GPU architecture. I think in my intro, we talked about 12. I'm not going to walk you through all 12, but I'm giving you some highlights for a purpose, so bear with me, please. So we've invested this energy and hardware and money into all of our GPUs having the ability to do general purpose computing. Mind you, no one was doing it. Yeah, there was students might do it, some enthusiasts might do it, but generally speaking, you buy an x86 processor. That's what you do. By the way, I love x86 processors. I worked at AMD as an x86 processor architect before I was at NVIDIA, so that's all good. But the goal was we wanted to enable markets that were not currently enabled just with PC gaming and 3D graphics. How could you get other people to use these GPUs for more general purpose computing? And what would these applications look like? Don't know, but you have, I mean, which comes first? You gotta have the technology there if you want people to use it. So the next architectures afterwards, what I'm calling the rise of GPU computing, how we actually started to go after it. So the next big one was Fermi, the GeForce GTX 580 Hsieh in 2010. So now we're up to 3 billion transistors. We actually now have very compliant floating point arithmetic here, including standardized in the 2008 revision of the 754 committee. Fuse multiply add was in there exactly as defined, in part because that's how we built it. We're up to 1,000 gigaflops now, teraflops, finally in 2010. So now we have this available. And what happened shortly thereafter? Now, hopefully many of you are aware of AlexNet. What happened in 2012? Alex Shashevsky, Elias Skipper, and Jeffrey Hinton, they asked themselves, these are researchers, and they were working on various types of hardware for AI-related networks, and they wanted to test out the power of their network. What if they used that network and entered the annual ImageNet competition? And so they did. They had their own model, their own neural network, referred to as AlexNet going forward. And they used those GTX 580s, 2 of them, the ones I just showed you, and it took 6 days to train their network on the data that they needed for the image competition. So you take the network plus one of these Fermi GPUs, and it blew away all of the other. So their results here are accuracy, top 5 error rate, lower is better. And they were far lower than anyone else who was entering the competition using more traditional image detection techniques or image classification techniques. This was the aha moment for the industry when they said, wow, this stuff could work. Like, we didn't think this could be possible. But again, if you take networks plus computing power plus data, look at what you can do. So Jensen, the CEO of NVIDIA, he refers to this, maybe others do as well, as the big bang of deep learning, when things really start to take off. And in fact, if we kind of look at it this way, you can see this blue curve here shows the trend we were on CPU-based scaling as we moved from the 90s all the way up to the 2020. We were going up about 1.1x per year in terms of delivered computing power. But now that we've enabled GPU computing, we found ourselves on a much steeper slope, about 1.5x per year, starting at this time when we were actually having general purpose capability in our GPUs. So again, you combine this computing power here with all three together, and that's the big bang of deep learning that happened. And there's our fly. Okay, that's fine. I did warn you, the lens on my head. Come on. Right. So Fermi was a great GPU for delivering on this functionality. It had its warts. It wasn't the most efficient engine built. So a couple of years later, with a ton of pain and suffering by the engineering teams, we built a much more efficient GPU architecture called Kepler. We made things run faster, lower power, smaller. We're up to 4.3 teraflops at this point here. Big GPU here, whole family of Kepler GPUs. In fact, in 2013, I think there was a question earlier in a smaller session, what about high performance computing? So in 2013, the world's #1 open science supercomputer was in fact a Kepler-based supercomputer that occupied this huge room, big massive set of all of these systems with 20 petaflops of computing power. Put a pin on that number, 20 petaflops back in 2013. Okay. So at this point, by the way, I just want to say, right about that point, the whole company started to say, deep learning, it's all about AI. Specifically, our CEO drove it down to the whole company. We're going to focus on building our GPUs with an eye to deep learning. Because we just saw the big bang, we knew things were expanding. That's where our focus needs to be. So we did. So our next generational architecture, Pascal, the P100, started to add FP16, smaller data type. I'll talk about it a little more in a bit, so that we get 19 teraflops of it for deep learning training and inference acceleration. We had higher bandwidth NVLink interconnect. We have even faster high bandwidth memories. So this was our next big, really AI-focused GPU. Again, going from single precision focus, at least now we're at half precision FP16. Okay, so that was, and then we said, okay, that's all good, but let's really focus on AI now. So accelerating AI with tensor cores. So in 2017, we launched the Volta architecture. And with it, we productized the concept of a tensor core. Now, if you recall, we were at 19 teraflops. Now we're up to 130 teraflops. And how did we do this? Is it just a bigger GPU? Yes. Is it in a smaller technology? Actually, let me just go back. Yeah, same technology. I forgot exactly. They're all in 16 FinFET. More memory, more interconnect bandwidth, NVLink. But we specifically we engineered, innovated, produced the idea of a tensor core, which was a specific computing engine rather than just doing SIMD or even scalar or SIMD style math, was doing an entire dot product, an entire tensor's worth of math together. You can see how Pascal would do it. Whereas with a tensor core, you can do the dot product, the tensor core dot product, all of them parallel, optimized for deep learning. What is it? In Volta, the tensor core looked like this. Big linear algebra, matrix multiplication, and accumulation. But we did it with mixed precision. The idea being that the weights and activations may start out in FP16, but we would accumulate through the network in a wider format, in this case, FP32. In fact, you could accumulate in FP16 or FP32. But the idea then is with these with this tensor core, you could take, like I said, FP16, full precision product internally, summed with an accumulator with some intermediate. So you have all of these terms in parallel, accumulate, and optionally convert or output in FP32. So by doing this with tensor core, they amortize the area and the overhead of doing instruction issue, all of the stuff in the GPU that isn't actually doing the computation. How can we just do more computation with less overhead? And so what we did is by doing that, you amortize the control area powers, instruction overheads, and we reduce the net energy per operation. So in this way, if what we really need is fast linear algebra, how can we get more efficient linear algebra to accelerate AI? And that was Volta. Then a couple of years later, this is roughly in the 2020 timeframe. Now I skipped the Turing architecture. I don't know if people are familiar with Turing. That was there too, but let's go right to Ampere, the A100. Now we have even bigger GPUs. We're in 7 nanometer now. We have our third generation tensor core at this point. We had our first generation. I kind of skipped the second. We're now at our third generation tensor core. We have HBM2E. We have really high performance memories. And we're up to now 310 teraflops and 600. I'm trying to make sure I get my math right. This is dense versus sparse. So the ability to optimize for sparsity as well. When you have sparse data sets, you can actually compute twice as fast. So now we're at 620 teraflops. You keeping track of this as we go here? Again, the idea is we're trying to, as fast as we can, realizing that the goal here, if we just build it, there are going to be more applications that can use it. And then just a little over 2 years ago, we launched the Hopper architecture, the most recent implementation known as the H200, which by the way, previously those numbers were FP16 accumulated into FP32 teraflops. But now we're up to 1 petaflop and 2 petaflops sparse of FP16. But in Hopper, we launched a 4th generation tensor core with 8-bit floating point. And we did, so this is the first version was back in 2022. It wasn't brain dead obvious that that's something that you should be done. It took a surprisingly amount of work. Should we do this? Is this a path we should go down? Does it even work? Right? That's always the question. No one's going to get fired for doing their work in FP32. We've already said FP16 works. The question is, well, can we make 8-bit floating point work? We said, well, we did simulations. Well, yeah, we think it can. But honestly, unless you build it, I don't know if they're going to come. We just got to build it. So we built it with FP8 here. And now with FP8, you're up to 4 petaflops. Remember we started like way in the megaflop, the small gigaflops, and now we're up here in the petaflops. So again, we have an even new memory system. We're the world's first HBM3E with big L2 caches. Again, you need everything for this to work. You don't need just huge computation. You need to have very high bandwidth connections, high bandwidth memories. And since you can't compute everything on one GPU, you need to be able to have fast interconnect to have one GPU talk to and communicate and work well on the same program, on the same problem sets with other GPUs. So we have our very higher and higher speed NVLinks that connect GPU to GPU. It takes all 3. Okay, so how are we doing time-wise? We're doing pretty good. So this took us to February, like literally about 2 months ago. By the way, so you see on the news, Hopper, how do I get a Hopper? I need a Hopper. Everyone wants a Hopper. Right? You may have seen that. I don't know. Even this department, I think they're trying to buy a Hopper. I think they got one at least. I think you have at least one Hopper here. Getting them. They're hard to get because it's really hard. These are big chips. Did we take a look here? This is TSMC 4N process, 80 billion transistors. So these are big GPUs. They go into big systems. They're expensive, but they do some incredible amounts of computation and interconnect and memory interaction. So I talked about the arithmetic and why we were able to do this. I just want to make sure I drive the point home here. We wanted to make sure that all of these formats were available to users, to developers to see, if you build it, will they come, can they make use of it? So we knew FP32 worked. I don't know, I'm presuming you all have worked with floating point in some form, so this is just a quick refresher. There's FP16 and BF16. Both are 16-bit formats. They change the number of bits used for exponent and mantissa. And then we proposed two different variants of an 8-bit floating point format, E5M2 and E4M3, either a little more exponent, a little less mantissa, or vice versa. And generally speaking, in the loop of training, in your forward pass and your back prop passes, generally forward, the numbers generally can be, the dynamic range necessary are such that 4 bits of exponent can generally be enough, or maybe enough. But for the very small values of the deltas that are computed when you do the back prop, you really need to be able to tease out very small differences. And that's where the extra bit of exponent is very helpful. So you provide both, and we find out what can work, right? You try things and see what works, and you provide both. This was actually standardized in an OCP, under the OCP Open Compute Program. I forget that's what the P stands for. You can Google that. NVIDIA, myself, others were in the standard, working with most major companies to standardize this FP8 format. So, again, walking back, see what's happened here as I've walked you through from Kepler to Pascal, Volt to Ampere and Hopper, and these more, not only the blue line was pre-tensor core, the growth in computing. Once we hit tensor cores, you can see we've gone even steeper in the ability to provide training computation. And we've been building these bigger and bigger data centers as we've been enabling these bigger and bigger computing engines. There was Saturn, there's Selene, EOS. But then, as I said, that was February. But then just a couple weeks ago, we launched Blackwell. Boom. Boom. NVIDIA Blackwell, which we're calling, so shameless plug, bit of marketing stuff here, but hey, it's technical, so I'm just letting you know here. This is the engine of the new industrial revolution, how we're referring to it. Now we have 20 petaflops of AI on a single GPU. Remember that supercomputer in 2013? That was 20 petaflops. This is 20 petaflops on a single GPU. How do we do that? I'll get into that in a moment, but what that's going to generally do is 4x the training performance versus Hopper, 30x the inference capability, 25x energy efficiency, and total cost of ownership. And it enables us to expand the data centers even much, much larger. How do we do it? Well, 208 billion transistors, that's a big part of it. We have this, remember, I didn't talk about it explicitly, but in Hopper, that FP8 is actually wrapped around and productized as a transformer engine, because that's the intent, is to accelerate transformer networks. So with Blackwell, we have our second generation transformer engine, where we introduce, not only do we have FP8, but we also have FP6 and FP4. And by doing that, that's what enables us to go up to 20 petaflops. We have even faster interconnect and a wide variety of other things that go with it to make sure when you start building these huge systems with literally hundreds of thousands of GPUs, you have to worry about failures. You can't just have GPUs going down into these big centers. So we have in-system self-tests, all sorts of things that are necessary to ensure that the machines stay up, that they're secure, and to make sure we have enough bandwidth. I mentioned I was going to tell you how did we build it. So we actually build it as 2 reticle limited dies that are then connected with a high bandwidth interface in between them. So you can see reticle die 1, reticle side die 2, high bandwidth interface between them, with 10 petaflops of FP8 and 20 petaflops of FP4. Of course, we have very, very deep HBM3 high bandwidth memory, high bandwidth, and 1.8 terabytes per second NVLink. So the idea here is full performance, no compromises. This thing just kicks whatever. It's fast. I mean, if you just look at it, just very clear here. For FP8, 2.5x die, single GPU to single GPU, 2.5x Hopper in terms of performance at FP8. With this new FP6, it's at the same speed, but it takes up, its footprint in memory is smaller. It's only 6 bits rather than 8 bits. So while the computing throughput is 2.5x of Hopper, the total delivered performance is actually higher because it requires less moving around, less memory, less interconnect bandwidth. And then we introduced new FP4, which doubled it again. So now we have 5x the throughput of Hopper, 20 petaflops, like I said. It used to be a massive supercomputer requiring huge centers. Now it's in a chip. So putting it all together, that's what the curve looks like. I tried to walk you through that so you could see, just going back to 2016, what the supply of computation looked like, 1000x in 8 years. So because it's the availability of this computational throughput is what is helping to enable these applications that everyone is very much fond of, the power of transformers, large language models. This is what it takes to be able to enable that and realize that. So how do you actually then use these building blocks to build these huge data centers? So I think in the earlier session, we were talking about what is the definition of a GPU anymore? Is a GPU just that chip? I don't know, did anyone happen to catch the actual Blackwell launch on YouTube or anything like that? You'll see that our CEO, Jensen, he actually picked up a Blackwell and showed it to people, and he says, $10 billion. That's what it costs to build one of these things. And he isn't wrong. It takes an inordinate amount of engineering to everything it takes to build one of these. Everything, all of it, the GPU and all of the things required to do it. So since you don't want to build an entire data center out of single chip boards, like maybe when you buy your GeForce, for those of you who are gamers, you don't want to put them all together as lots and lots of single die. So instead, what we built is a GB200 super chip, which actually comprises 2 Blackwell single GPUs combined with a Grace CPU. That's the NVIDIA also builds. If you don't know, please, you can go to the NVIDIA website. We also build high performance ARM CPUs. So we have a single super chip that comprises both of those. So it combined has 40 petaflops of FP4 for inference and 20 petaflops of FP8 for training. And then you can then take 2 of those together, combined with the appropriate amount of memory. And then at this point, so you now have effectively 4 GPUs in one tray. And then you can take those trays and put 18 of those trays together in a rack. So now in this one rack that you can build with just 18 of these trays, you now have for training 720 petaflops and 1.4 exaflops for inference. So 36 Grace CPUs, 72 Blackwell GPUs, all fully connected with NVLink. Model size here, this is an actual product. You can buy an GB200 NVL72. It's this whole thing. So depending on the definition of a GPU, some would, in one embodiment, this is a GPU. This is one atomic unit of work that you can literally go buy, and it's all packaged up and ready to go with this level of crazy performance and memory bandwidth and interconnect. What does that mean if you start building using these NVL72s? Like I said, on a state-of-the-art, huge 1.8 trillion model network versus Hopper, we can actually train 4 times faster. That's a big deal. That can be, instead of being a month, that can be a week. Instead of a year, and so forth. Inference is actually truly, really incredible. If you look at what's possible here, again, it's a combination of higher throughput with computing, interconnected memory, all of these together. If you look at with a Blackwell versus a Hopper, it's computed die to die, but if you build up the same size systems on a kind of a earlier 175 billion parameter network, about 6 times faster than Hopper. But if you use a modern 1.8 trillion parameter network, 30 times faster inference and 25x improved energy efficiency. So yeah, 25 times less energy, and for the business-minded, 25x lower total cost of ownership. So Blackwell is a, yeah, let me come back here. Just to conclude here on this topic, Blackwell is a pretty big deal. You hear about it. Hopper was, all of these were big deals at the time. And my point in walking you through this is just to show you some of the strategies that were deployed and the mindsets and the decisions that we made along the way, such that it wasn't that just, wow, one day, hey, they got lucky. They just happened to have this thing that people like. These were concerted efforts over many years with decisions made in investments in hardware and software. So again, tons of innovations in hardware, CUDA, libraries, platform to be able to make these systems possible. So especially for any of you, I think a question was asked, going forward, should I focus more about hardware? Should I focus more about software? By the way, it's all good. There's demands certainly in this domain for both. I will say that you can almost never go wrong with being a fully capable software engineer. That will certainly float almost any boat in terms of being able to work in this space to make bigger and faster AI networks and platforms. So coming back to some of the work that my teams at NVIDIA have done, working with other teams at NVIDIA, are applications of AI for chip design. One of the projects we did a couple of years ago, it's called Prefix RL, where we did circuit design with deep reinforcement learning. And what we did is, this is a graph of, this is your delay area Pareto curves, looking at the trade-off of as you build, this is for integer adders. What does the trade-off look like? And you want to be down and to the left. You want to basically build things that are infinitely small and take no time. Generally speaking, this black curve shows what your best state-of-the-art EDA tool would be able to build for you. But we actually then applied reinforcement learning, trained on adders to see, can we do better? And you can actually see how the network would actually build up and come up with idea topologies that are beyond what even the EDA tools would come up with. As a result, by using this technology, we could get about 25% lower area at the same delay. And we used thousands of these circuits in the Hopper architecture, and some of them I believe carried over into Blackwell as well, using this prefix RL technology. We had a paper on this at DAC a couple of years ago. So that's kind of that was a pre-large language model use of AI internally. Something more contemporary that we're deploying today is a whole package of work called ChipNeMo. ChipNeMo is a rubric that defines basically AI for chip design at NVIDIA. The first instances of which include a chatbot, code generator, and bug analysis tool. So for example, the idea which is gaining more prevalence, you're familiar with your chat GPT, maybe with Microsoft, with Copilots, the ability to always have next to you an expert. Now the thing about ChatGPT or Gemini or Claude, depending on which version you want, they're good. In many cases, they're very broad. They don't necessarily have extreme depth in any given discipline, although they're certainly trying. The models are getting big enough that you can actually get a lot of depth. You can pass law bar exams, MCATs, all sorts of very technical things, even with the broadest networks. But what about if you want to have very specific, like for your engineering department, using on your workloads? Where is that senior engineer that I'd like to always have next to me, who can always answer any question that I have? And certainly neither OpenAI nor Anthropic nor Google will have that information. So we're building ourselves copilots, chatbots that have that capability, that they can act as your engineering assistant in your domain. So that's certainly a key area. And we see this happening across industries. Pretty much every industry is going down this path of trying to create copilots, chatbots that have domain expertise in whatever the given industry is. So that you don't need to always say, hey, where is that, Joe or Jill who's been here for 25 years, who knows where all the bodies are buried? The chatbot knows, and you can go to him or her and give you the right answers. We have code generators. Here's an example of a particular focused domain script generating tool that we're using, where it's used for back-end physical design, for finding cells and perhaps doing timing fixes on it. It can be very tedious to try to do all of that by hand and write the typical type code that's necessary then to drive the engines. Here you can just say, you can ask it and interact with it in natural language, and it'll do all the work, code generation. So certainly code generation in general is another great area for large language models, because at the end of the day, an LLM just sees vectors and numbers. It doesn't matter what language. That goes to the multimodal concept I talked about at the beginning. So getting depth and knowledge in any one language often applies into others. So even our big general purpose networks are familiar with coding. They've trained OpenAI, Claude, Gemini. They've all been trained with software engineers to do well at very general programming problems. In many cases, they can even do hardware design languages as well, but not necessarily very specific, domain specific. And finally, again, another thing that if you don't already use yourself, I certainly do, is the ability to do summarization. One thing you do, you get a new type for those who are grad students, you get a new technical paper. Maybe your advisor says you got to review it. Maybe it's a peer. I don't know. I have to spend often myself as a paper reviewer. I spend 20 minutes like, okay, what is this even thing about? I can't go technical. Yeah, I just have to figure out. You read the intro, you go to the conclusion. You're like, okay, what are they trying to do here? Okay, this is okay. Yeah, I get it. Fine. Now let's go back and walk through it. Large language model. Give it the paper. Let it summarize. It does all that for you. That's there today. If you're not using it in that fashion, just any of the broad tools. Most of them have PDF readers and things where you can just pop out a PDF and it'll pop out a summary. So here we also use that more pervasively within our company, where we can take, for example, design, software, hardware bugs. They could be pages and pages long of comments of people working on it. I come into, hey, Stu, you need to come in and try to fix some of this. Your expertise is needed. Really? I have to wade through 10 pages of bug comp to figure it out? No, use an LLM. It'll summarize every point. Okay, here's where we're at now. Great, I can jump right in. I can get going. So summarization, another great aspect that, again, we're using ourselves. But these are just starting points for ourselves, but I can see these being more widely deployed in the industry as well. Challenges and opportunities. I think I'm almost done here. Two things. One is Moore's Law dead? This is, by the way, rather a religious construct that's out there, because our CEO famously has said Moore's Law is dead. And we certainly act in that way. There are others out there who say, man, I don't know what he's talking about. It's not dead. Interestingly enough, they're both right, but for different reasons. The reality is, what is the definition of Moore's Law? I presume you all know Moore's Law in your UWs, right? Okay. It did help to fund most of the massive increases in transistors and teraflops that we talked about. To be fair, that curve, a lot of that was Moore's Law. By the way, Bill Daly, chief scientist in NVIDIA, I didn't swap his figure here. He gave in his keynote at Hot Chips, he broke down in his mind kind of how much of it was technology versus the right-sized arithmetic versus architecture. You can argue about how much of those improvements were really due to each of those. And they are all big contributions. Right-sizing arithmetic, Moore's Law, great tensor cores, doing things smarter, they all matter and they all improve things. But the reality is, we used to be getting that increase in transistors for free. We used to be basically saying that the cost, the dollars per transistor was going down over time, which meant I could, for ISO dollars, I would just get more transistors. That's awesome, especially as a gamer. If I can get a new GPU for the same price and I can run 50% faster, twice as fast, that's an awesome bargain, right? Moore's Law funds that. Not anymore. It's not that we can't get smaller transistors. We can get them. For the more physically oriented folks in this room, you're probably aware of all sorts of more exotic technologies for getting transistors and dies put together, whether it's in 2 dimensions or in 3 dimensions, to get more effective die areas. Those all exist, and we can have smaller and smaller feature sizes. We're not done. There's 5 nanometer and below, but they've gotten very expensive because building up the gates in these exotic small transistors, given all of the physics that comes into play, it's really hard, and that doesn't come for free. So the challenge is, it's not that we can't get more transistor budget, it's just really hard and really, it starts to get very expensive. So we have to think about that very carefully. How do you engineer in this world where it's no longer cheap and easy? Now you have to really put in engineering effort at all levels. Something to think about. Other things. Again, these models, they're growing, they keep growing. I guess we said if we build it, they'll come, well, they'll keep coming. So that's going to vicious cycle. It's a good one. It's going to continue to have higher requirements on GPU performance. If we want to actually be able to deliver these things with any sort of efficacy in terms of being able to build the chips, you have to worry about performance, power, and area. Incredible attention to PPA, as it's known as. You building these large GPUs, we didn't even talk about this really. How do you actually make sure that they work? 208 billion transistors. Spoiler, that's a lot of transistors. That's a really big chip. And they just keep, how do you think that works? Tons and tons of pre-silicon verification is required, and performance verification to make sure that these things actually can work first silicon out the door and go. But yet that's what needs to happen to be successful. And finally, how do you even do hardware design entry anymore? Does it make sense that we're still coding in system Verilog? Should we be using other higher level abstractions? For example, a large language model for code generation? Sure. These are just some of the challenges and opportunities that kind of I'm always thinking about, but maybe it'll inspire you to think about some others for yourselves as well. So I believe that ends my prepared remarks. So I did warn in advance, since you're students, you may be interested in doing work of this sort. Maybe in the future, sometime you will graduate. If you have power to you, hopefully you will. So what is available here? I just want to let you know, as it turns out, NVIDIA is actually doesn't have just cool technology. It's actually a really great place to work at. If you look at depending on where you're at, if you look at Barron's, Fortune, Glassdoor, for those of you who are looking for work, you often use the real dirt you'll find on Glassdoor to see like what other people really think. It's rated, I don't remember which year, one of the best places, if not the best, as rated by its own employees. The CEO, Jensen, continuously put out there as being one of the, if not the world's best CEO. It's a really good company to work for. Founded in '93, Jensen's the founder. We're up to, I think, even close to 30,000 employees now. By the way, that's just, I'll go back to it. That's actually, so I don't know if you, in Santa Clara, we have two big headquarter buildings. We have Endeavor and we have Voyager. So we actually have a really cool building. You can take a virtual tour through it online if you want. Flyovers. It's really cool. We have a big opening. It's a very open space. Here's at a company meeting. That's Jensen on stage here talking. It's a really cool place just physically to be as well. Not across the board. Not all Silicon Valley, not all tech companies are pervasively hiring. NVIDIA is. We are hiring. Our work is transforming the world's largest industries. So links here, please go check it out. Depending on where you are in your journey, in your academic journey, probably most folks are beyond your second undergraduate year, but we certainly have all sorts of internships, new college grad, both MS, BS, MS, and PhD. I'm guessing many of you have already, from what I've heard, many students have already interned there, or a lot of alumni have gone on to become graduate employees here. That's great. All sorts, you say, like, yeah, but what kind of jobs? We kind of got everything. We're trying to innovate in all these different spaces. You want old school computer architecture? We got that. You're like, nah, I'm a hardware guy. That's great. Hey, I'm a hardware guy. So the teams I lead are actually doing the HDL verification, the PPA work. That's what my teams do. I'm responsible for a lot of this. But hey, I'm a software person. I really want to innovate at the model level, come up with new sorts of. That's great too. We have huge AI teams, both in development as well as in research. So we have R&D. So if research is the way you like to go, we got R. You like D, we got that too. Software, I just want to build compilers, we got that too. All sorts of good stuff there. Thank you.
So we have some time for questions. Maybe technical questions first.
I wanted to ask for the Blackwell and I guess the previous models, you guys focused down on transformers specifically. Were there any concerns that transformers, like there may have been like a second transformers moment where like another type of LLM, you get where I'm going with.
So I think the question you're asking is, how do you decide what do you focus on? Like we have a code of conduct at the company where we have specific, should have it memorized, all of the 5 items. One of the biggest ones is agility. So everything we do is with agility in mind. So it didn't just happen, by the way. It wasn't like necessarily the transformer thing was like planned out years in advance. We saw that something was happening and we moved really fast. I'm not going to tell you exactly how fast, but we moved shockingly fast in the shipbuilding timeframes to actually put stuff in. And if we see that something else is happening in the market that needs to change, we move really fast. A lot of us, myself included, I didn't talk about it, but many folks have worked at startups. I continue to, many of us call it, it's really the world's largest startup because we move really fast. This is not big bureaucracy where you need 10 VPs to buy into all of this. You got an idea, boom, boom, boom. Hey, Jensen, what do you think? Yeah, looks good, boom, ship it. That's almost how it works. Not quite that fast, but the point is, we're very mindful that the world's moving pretty fast. Remember Ferris Bueller? Life's moving pretty fast. You got to stop and look around. So we do that all the time. It's called being alert and being agile. So we're always looking what's going on in the world. We measure ourselves, by the way, not just about the competition. Again, if you know anything about NVIDIA, you'll have heard of the term of speed of light. We always measure ourselves against what's the best that anyone could possibly do. And we were always measuring ourselves against that. And then we say, if we find that we're veering, we're too far off in a particular area, we know we're exposed. If the new technology comes out and we think it's sufficiently important that we innovate there, boom, we move. So if there's a new model comes out or something, you can bet that we're going to be moving on up like that.
I guess the question is, were there concerns that a new model would have evolved before the chip came out?
That's why we moved really fast. I'm not kidding when I say how fast we I mean, obviously, if you tape out in month X and there's a new one in month X plus 1, hard to beat that one.
Right.
Yeah, so there's some exposure. There's some full-time requirement for it. Yeah, question.
From your introduction, it almost sounds like the most recent 4 or 5 generation of GPUs, the advancement is based on supporting a lower precision. Like, because you're showing improvement on floating points operations per second, but in fact, those floating points, they're not exactly the same. You're supporting lower and lower precision.
Right.
You're kind of like relying on supporting lower precision to get better performance for your latest GPUs. Is that correct?
The terminology I used was right-sizing the arithmetic. And I think, as I mentioned, in Bill Dalley's talk, you can check on YouTube's keynote, he talks about how much of the benefit you can really derive. A lot of it is, you're correct, to right-sizing the arithmetic. That's not a bug, that's a feature. I mean, that wasn't accidental. We have people working in computer arithmetic thinking about this stuff and thinking, what's the right size? Figure it out. And that's what we did. And then you figure out, work with the industry to say, can this work? So it's not, and you work yourselves. You have your own teams of researchers trying and simulating models. Can we get these things? How many epochs does it take to train if you go instead of 32 bits, you go at 16 or even 8? You try and you model it and you see. So yeah, it is a big deal. Right-sizing the arithmetic matters. Yeah.
When you spoke about the chip demo, so in that you said that we have a code generation for the hardware. So it's often the case that hardware itself is the most confidential thing. But when we use chip demo, are we making the hardware visible? So how do we deal with the? Yeah. So regarding this, so we basically have like the code generation itself, or the hardware code generator in it.
Well, this doesn't show any code generator here.
Or specifically.
But you're saying if we had one.
Yeah.
Okay.
So that would expose how do we deal with the confidentiality in that case?
Well, I mean, it's a tool that's only available. I mean, it's an internal tool.
Yeah. So in that case, like if we are providing it as a product, and in that case, like
it's not. These are internal tools. These aren't products. There are products out there that do code generation. For example, most large language models will do some amount of code generation. But what we're talking about here are domain-specific, proprietary. Like every industry is going to have their own proprietary data. At the end of the day, what's the most valuable thing in all of this? It's usually the data, the expertise within the institution. And those are not going to be freely given out. It's the data. I mean, that's the whole social media expense, right? If it's free, that means you're the product. It's your data that they're actually using. So in this case, no, that data is expensive and it's kept within the company. Yeah, question.
Just facing this, how would you position a researcher or a developer having a chatbot, having a code generator, having a thought summary? Because how I see this is that the researcher, the developer is more like an observer for a autopilot situation, and one sometime later is gonna be useless. Or do you think there's more to it that's
you're worried that, take for example, the expert engineer co-pilot. You're worried that his or her knowledge, the chatbot's knowledge is going to get obsolete?
No, I'm talking about the developer.
The developer.
Yeah, the engineer.
Yes.
In this case, would be obsolete at some point.
Oh, is AI going to get rid of engineers?
Yeah, because
That's a real risk.
this is a pipeline going
Yes.
on.
Yes. Spoiler, this is a big deal. If you're not reading about it in the media, you should be. I mean, yes. I mean, AI has the potential to greatly reduce the demand for human engineers. Yes.
Then how do
I'm not passing judgment, good or bad, on that, but that's a fact.
How do we position ourselves in this case to not be obsolete?
Up level yourself as much as you can and recognize the power here so that you can be a user of it, not one that gets flattened by it. It's reality. I mean, this is as I told you, it's a new industrial revolution. So there's so much work that needs to happen. I mean, if you want to stay in this domain, by the way, that's great. It's not like this is going to be solved. I told you, we're hiring. Remember that? Other companies are hiring. There's so many startups, people working on AI. So there's all sorts of stuff. Software engineers specifically, for example, I don't see that being completely auto-generated as a level of a professional engineer, not in the near future. Our CEO, Jensen, has famously spoken saying, stop learning how to code. You don't need to. Up-level yourself into the other domains. I think that's probably correct in the long term, but I mean, there are long careers in front of all of us here where I don't think that's going to happen, say, in the next 5 to 10 years. But in 20 years, I don't know. No one knows. I'm alerting to you all, if you haven't seen it already, that this is the technology that exists. It's exciting. It has the capability to do things that heretofore were unimaginable. But it does have some real life impact, even to ourselves directly. Think of it as an awesome tool that you can use as an amplifier of your skills, rather than as something that's going to replace you. Because that's what you should be. You already do that, right? I mean, there are so many, even in chip design, there were full custom design engineers who were like, hey, the synthesis tool is going to take away my livelihood. It kind of did for those folks, for those of you who remember logic synthesis and its innovation. But then you retool and you're like, okay, I found other ways I'm going to work on logic synthesis instead, and so forth up the chain. There's not a huge demand necessarily for ports and buggy at the moment, right, drivers, but we found ways to innovate and to adapt to these changes. Yeah. Yes.
According to the previous one, my viewpoint is that you see, like during at least the next decade, there would be a huge effort in actually like building the facilities for like this area, because they need like huge facilities and optimization.
Power and cooling.
Power and all of the things you said, like at least 10 years. And after that, we might see like the effect that we need, like like the AI can do like the like passing, like pushing forward itself. But until that point, I think like we will see some shifts in like what like people or engineers do. Yeah. But still we will have a lot of like work. But probably like as you said, like with dynamicity, like different.
Yes. Remember what I said, key points that work for the company code is for yourselves as well. Be alert and be agile in everything that you do. Don't get too settled on this is what I'm going to do for my life, because you have to be able to adapt. So the one thing sure in life is change, right? The stuff's going to change. So this is true as of April 2024. Check back in a year. I'm guessing in a year things could look drastically different. So no. Any other questions?
So you didn't like big trend throughout the years is that these chips have been getting bigger and bigger, right? These GPUs have been getting bigger. We have new chiplet design that many across the board are implementing, and transistors are getting smaller and smaller. But kind of like I don't know if we're saying approaching a limit, but like 3 nanometer is pretty small. And in terms of like the actual, for Blackwell, you guys maxed out the reticle size for both chips, right?
Yeah. But we've been maxing our reticle. Everyone has been for some time.
Yes. But like, what is next in terms of like for getting the chip bigger, or like is it like 3D or like what?
Yes. Yeah, I mean, I talked about that. That's an area of open challenges and opportunities. How do you keep meeting the performance needs? Bigger could be one way. There's all sorts of angles on which you can think about perhaps trying to meet the performance requirements going forward. It's not going to get less. So, I mean, that's like you can see here, there's real engineering work that needs to happen. There's a reason why we have all this hiring going on. It's hard.
Thank you.
Following up on this question, so from the angle of precision and arithmetic, you guys maxed out what you can do with respect to the number formats. I've seen like in Blackwell now we've gone down to FP4. Or is there a push? You tended to talk like a couple of years ago for Bill Downey, he was talking about maybe looking into logarithmic number system or different types. Is this still a thing?
So for those who couldn't hear, what other formats can we use? Log, otherwise, those are all great ideas. Yeah.
But we've reached a limit, right? Like a couple of bits.
I mean, we've reached limits long ago in many of these areas, and yet we still keep moving forward. Humans we love to innovate, right? That's what you're all here for, right? You're learning how to be engineers and innovate. Yeah, whenever people say we've reached the end, like, don't say that, because people will find a way. A lot of smart people like yourselves in USC figuring this stuff out. So I challenge you, please work it out. Help. Maybe.
Yeah. So adding on to the same question that we're all discussing, I had a chance to view the GDC event as well. And in the event, I heard Jensen say that NVIDIA is even partnering with like Cadence and Synopsys to introduce co-pilots to EDA tools, right?
Yeah.
So, I mean, I'm guessing like, in a year or so, kind of roles that people usually hire would eventually change with the introduction of this. And is NVIDIA still partnering with Cadence and Synopsys to like work towards this field, or is it like specifically a small team that's working?
I mean, if Jensen said it, it's so, right? I mean, yeah, what he said is correct, obviously. That's not directly related to what I'm showing here. I mean, it's relevant and related at the high level, but it's not specifically this specifically. But yes, I mean, I don't want to put too many words in their mouth, but I mean, definitely we know the EDA vendors are looking to do AI and have more AI-empowered tools. NVIDIA is an AI company, but it certainly makes some sense that there'll be some collaboration there. Okay.
Just want to give a chance to our online participants. So there's one question saying, what do you think of one API or UXL project? Do you think other companies will reach the same level of acceleration, potentially make NVIDIA lose CUDA's competitive edge?
Okay. So is CUDA a moat? Is that kind of what you're trying to ask? Or is it a moat that has been breached and now everyone can do the same thing? I mean, there was never a moat. The API was never intended to be like something that only NVIDIA can do. It was solving a problem and presenting it. In many cases, it was never. We look for hard problems and we try to solve them and deliver great solutions. That's what any engineer yourself should be doing. If there are other places that can do similar, better work, good for them. They should do it. I mean, that's engineering. Yeah. Do I think that this one thing is always going to win? No, I don't think so. I mean, I might hope so, but I'm an engineer, right? We know that there's a lot of smart people everywhere.
Very good. One last question from online.
Sure.
How long is the timeline of each processor NVIDIA make? If it's too short, isn't it countering the best work environment thing?
What was the last part? How long is each development, and is it canceling?
So I guess the question is that how long is the timeline? If the timeline is very short, doesn't that affect work-life balance?
Work-life balance. Yes. First of all, those are orthogonal topics there. Because first of all, as a manager, which is a term that I am one, solving work-life balance and getting work done is not about how short your schedule is. I mean, it's true, quick project management, triangle, scope, time, resources. Those are your three things you can change. You can say, well, if you make the time you don't have enough time, what are you going to do? You're going to make it really bad for your engineers. You can hire more engineers. You can change the scope of the project. There's things you can do. So yes, as a project manager, you clearly have to always have your projects not only be what the world wants, but also what you can reasonably deliver. And I did show you, just to toot the horn one more time here. That's by the employees, right? So it's not just lip service. The people actually think that this is actually an okay work-life balance. Can work-life balance in any engineering organization be strained? Yes. You could have particular projects that aren't planned well. You could have things can happen. I'm not in any way giving a blanket statement. This is perfection. I'm just saying, on the average, things are pretty good. And situations like that can always happen, but you always work as a project manager to try to solve those. Okay.
How long
I probably got like maybe 1 more minute.
1 more minute? Okay.
Yeah, so maybe
one
one
last
more question.
question.
I think you were asking before your turn.
So mine is like a non-technical question.
Okay.
So tech is not FMCG. We have seen companies rise and fall. Seen companies, IBMs, Intels. I'm not writing them off. I'm just saying that they also wanted to be nimble. They also wanted to be agile and move fast.
Yeah.
But they have they are not in the mainstream now. They are not the elephant in the room. NVIDIA is now the new elephant in the room. How do you see? How do you cater to this kind of dilemma of being the market leader and being disruptive?
If I were to, I'll actually replay words. I was at a gathering with Jensen. Sorry to quote him, but he's got a lot of good wises, and I was telling you about that. I mean, that's what scares him and us pretty much every day. I told you, you need to be alert and you need to be agile. You can never rest on your laurels. That's true for in any work that you do. You should always be mindful of threats and being alert to what's out there. So if you're asking me for guidance for what should Intel do, I'm not sure. But if you're asking how to, NVIDIA's mindset, mine personally, is always be alert to what's out there, be ready to react, be agile. And if something comes along that's going to be better than your technology, you better invent it first. You should be the one obsoleting yourself. You shouldn't ever let someone else obsolete yourself. Okay? I think we're about out of time there. Okay.
Yeah. Thank you very much.